So here is the previous structure like in Uber. So QR as a query runner, which is an upstreaming queuing system of Presto. And we have two main different type of queries. One is for interactive, one is for batch. Batch is mainly for the scheduled queries, and interactive is like the user are sending the queries and waiting for the response. So when the query comes in, it will go through the user and source limit, and then pass to the cluster limit. So if the query can pass this limit, and it will route to any available cluster in its belonging group. So in this structure, as you can see, actually the queries are sharing the queuing system and also the resource despite of the cost of the queries. So there's a very common use cases is like the user submit the small queries, which normally can finish within seconds. But because of the peak, during the peak time, the cluster is very busy, and we also have this limit. The query actually queued for like around 20 minutes. And this is not only one user having these issues. Actually, in our analysis, more than 50% of our batch queries, their execution time is less than 2 minutes. But as you can see in the queue time for these short-running queries, even during the very high peak time, it's around 20 minutes. And even worse, actually, we have some queue size limit, which is set it up in the QR side. So the user are sending queries which are pretty small, but they have to queue because the resource limit, and they have to ask the query runner team to provide it more even higher limit because of this huge whole system's limitations. So this is where the Presto Express project come from. So we want to improve these use cases. So the first things we did is we want to prove like the high concurrency for short running queries is possible. So we did some experiment for this, and we route like the short running queries which their runtime is less than 2 minutes from two full size of clusters, which has 450 hosts, to a staging cluster which only have 70 hosts. So this graph is showing like in that 4 hours shadowing period, the query count, which is for the staging cluster, it should be the blue bar, is higher compared to the another two production clusters. So it gives us a hint like the high concurrency for short running queries is possible. So our next question is how we can define if a query is express queries or not. So here I want to introduce a microservice which is called Preon. So this Preon is designed for streamlined query analysis and workload management. So once the query is finished, it will ingest it to Pinot tables through Kafka, and Preon can run the Pinot queries to get the real-time insights. So right now we have all the historical data, and it comes to the next question, how we can define the express queries. This is the example queries that we use to define the express queries. So we do try to understand the P90 runtime of the abstract fingerprint in the past 5 days, and how many queries for this abstract fingerprint in last 5 days. If the P90 runtime is then 2 minutes, and we also have at least 2 queries, we are defining these queries to be express query. We actually did some analysis for different look-back windows, like 2 days, 5 days, 7 days, and also with P90 and P95 with exact fingerprint and abstract fingerprint. During our analysis, we realized that the P90 of execution time in the past 5 days with the abstract fingerprint can give us the best result of the combination of accuracy and coverage. So now we have everything. We already proved that the high concurrency for the short-running queries is possible. And also we realized like how we can define if a query is express queries or not. Then we come to our first attempt to enable this express cluster. So we take out one full size of production cluster as express cluster. And the rest of things are keep the same. So in our routing part, we are talking to Preon to see, okay, if this next coming queries is express or not. If it express, we will route to the express cluster. Otherwise, we will route to the regular clusters. As I shown before, like more than 50% of our queries are express queries. So that's the reason why we think like one full size of production cluster can help us handle all these express queries. But it's not that ideally succeed because of this underutilization issues. So as you can see in the first graph, this black line is the express cluster. The CPU usage for this cluster actually is 1/10 compared to the normal clusters. Even though it's running like 5 times queries compared to the other clusters, the CPU usage is still very low. And normally when we see this cluster always stay idle. This is because like the queue throttling overlooked. One thing we noticed that is our non-express clusters, which previously running the combination of small queries and heavy queries, right now only run heavy queries. And that caused the situation like the queries on this non-express cluster would take longer time compared to previously. So because, as I mentioned before, we have the user consumer limit and also the cluster limit. So some queries are staying on the non-express cluster are running longer time. That's why more queries are stuck into the queue. That's the reason why like our express cluster, which is always stay idle without no queries comes in. So how we improve this? So first of all, instead of only getting to know if this query is express or not during the routing part, we relocate the express determination to the beginning of the query flow. In the meantime, instead of using a huge cluster like 450 host ones, we starting using a small clusters. And last one, as we saw, like it's get overlooked because of the user and source limit. So instead of blocking them due to these limits, we want to have a separate queue and provide a higher limit to express queries. So here is our second attempt. So in the validation part, which is the beginning of the life of the queries, we check if this query is expressed or not through Preon. And we enable a separate queue called query runner express queue. So the light queries will route to this express queue individually, and the rest of them will route it to normal queues. And instead of having the user and source limit, we skip that part, but we only have the cluster limits. So we want our express cluster to accept as many as queries as possible. So in this second approach, we actually see the great improvement. So for the execution time, we saw like it's decreased around 50%. Even though the previous queries is already pretty small, but we can see like right now the execution time is decreased even further. And once we enable the separate queue, we also see like the P90 queue time is decreased more than 60%. So in a short sentence to conclusion, the improvement is that the express cluster running more than 50% of the queries 50% faster with only less than 55% of batch cluster resources. So this is a huge improvement once we enable the express cluster on our batch system. And also, we're also considering some next steps, some further optimizations for this whole system. The first thing is right now we only use the execution time, but we also want to consider using the CPU time, which will be more reliable. And the second thing is, right now we're only using the historical data to predict if a query can be expressed or not. So we're more relying on the historical data, but we don't know if the first time the query comes in, if it's expressed or not. So we also want to introduce a machine learning model to predict the query cost. And the last one is we want to improve the reliability of the non-express cluster without reducing the SLA by reducing the concurrency limit. Yeah, I think that's it for today. Thank you.